All right, so thanks, Isajan, for the introduction. Otherwise, I had a slide to introduce myself. So yeah, I'm a PhD student at COSIC. Before I was a research assistant at CISPA. And yeah, I mostly work on COED, so computational encrypted data. And specifically, for example, private information retrieval, where you query a database, but you don't want the database owner to know what you queried. And then a bunch of other stuff like transiphering, bootstrapping, PPML. If you want to learn more about these things, you can talk to me afterwards. So first, very briefly, some motivation. Quantum computers seem to be a credible threat against some conventional cryptographic algorithms. Although there's some nuance, people will argue that it's a threat now, only like in 10, 20, 30 years. But ultimately, it's best that we switch now already, just in case. And so there was a competition to standardize a bunch of PQC algorithms. And specifically, I'm going to talk about key encapsulation and digital signatures. And so this is the submission I'm going to talk about, so specifically crystals carbon, crystals lithium. And they were both submissions to the PQC competition that use module lattices and module LWE. I'm going to explain what that is in a bit. And so there's a large body of contributors, some of which you may know. And if you want to learn the whole thing, they have their own website with example code and the papers, etc. And yeah, both crystals carbon and crystals lithium were chosen for standardization amongst other algorithms. And so we're going to talk about those. So this is roughly the outline for today. First, unlike the first two presentations today, I will need to introduce some theory and other background knowledge. Then we move on to the key encapsulation mechanism, so ML-KEM, then signatures, ML-DSA, and then I have some concluding remarks and thoughts. So just had lunch, so we're going to start very slowly. So suppose you have a linear system like this. And I give you the A matrix of the system and the right-hand side. Can you recover S? Well, this should have been hidden, but this is often quite easy. If you do it over R, you just run Gaussian elimination if it's a square matrix. If it's bigger than that, you also have options. So that's still quite fine. But now let's tweak the game a bit. Say we, again, have some secret vector. And again, we build this linear system, but in this instance, we perturb it as well by a vector sampled from a special distribution instead of uniformly at random from R here. And so I ask again, how easy or difficult is it to recover S? Now, this is quite broad. Can anyone tell me an instance where this will be very easy? That's one case, yes. But there's others. I mean, one particularly easy case is if you do it over R, then you have anything from least squares, compressed sensing, Gaussian elimination, sometimes in certain cases, actually. If you work over Z, surprisingly, this can still be solved sometimes efficiently, though not in general. But the cases we care about for lattices, well, for the so-called learning with errors problem, which is cut off up there, we'll instantiate the system over ZQ, so integers mod Q. And on average, this is going to be extremely difficult if you pick your parameters properly. So the dimension n here, so the length of the vectors, the modulus, and a distribution. So if you pick this correctly, this is nigh impossible to solve, even with quantum computers. You can modify this game. There's also a thing called ring LWE. There, the vectors, they're just one element vectors, but the difference is you pick the elements from a polynomial ring. This is just an example. You can choose a different polynomial ring, but this is the one most commonly used since it's efficient to implement. And then there's also module LWE, which is kind of between the two. So you have LWE, where you have vectors of just integers. You have ring LWE, where you have just one value of a polynomial. Module LWE, vector of polynomials, because this forms a module. And so intuitively, you can say that module LWE is between LWE and ring LWE. And I can already tell you now that LWE people like because it's not really structured. So it's considered harder, whereas ring LB is considered very structured, so people think it might be easier to break. And in fact, there's a bunch of other variants. There's also LWE with sparse secrets, there's generalized LWE, and a bunch of other things. And so this is the lattice problem we'll need. Now, briefly, I'm going to also introduce some crypto concepts for people who may not know them. So broadly speaking, you have two kinds of cryptographic schemes for encryption. So you have symmetric key, where you use the same key for encryption and decryption. And you have public key crypto, where there's special keys for encryption and special keys for decryption. And then there's a bunch of other fancy constructions like threshold crypto systems, where you need a certain amount of decryption keys. Now, I'm going to show you an example of a public key system. And I'm also showing it because it's going to serve as a counterexample in many places. So this is RSA. Bart mentioned it earlier already. And so RSA, in encryption, we're not going to talk too much about generation here, just raising a value to an exponent. Decryption as well. And if you pick the exponents properly, they're going to cancel out up there. And RSA in general it's neat, it's quite elegant. There's a bunch of issues. And just to give you a few of them, if you, for example, pick the one exponent correctly, it's broken. If you have a poor RNG, then it's also broken. If your other exponent is too small, also broken. And in fact, there's like a 30-page PDF listing all the things you could do wrong with it. What is relevant to us is that, at least in theory, it can be broken with Shor's algorithm. Now, there's been a bunch of papers claiming to use their quantum computer to break Shor, but it seems like few actually implemented Shor itself. They may use sub-procedures from Shor's algorithm, like just quantum Fourier transform. But if you want to see the full discussion, there's a pretty good one there. So this is public key crypto. Now, this is old stuff. Now the new stuff. Can we use LWE to encrypt values? Yes. In fact, it's quite easy. So again, we build this LWE system, but just with one row this time. What that means is we sample one vector here over ZQ. We have our secret S, compute inner product, add the error from a special distribution, and this is often just called an LWE sample. And so there's a thing called regave encryptions, which is a basic way to encrypt values, and it just boils down to creating an LWE sample and adding a scaled version of your message. You may wonder, why do we need to scale it? Well, if we don't, we would add the message and the error here at the same time. And then once we decrypt, if we don't do the scaling, we would have no way of telling the error and the message apart. So we basically move the bits of the message up, keep the error bits down, and voila. To decrypt, we just subtract this inner product again and round it to the next multiple of Q over T. And this works as long as your choice of E is small enough. This is going to be relevant in a bit. Now, you can play the same game with ring LWE and also module LWE, where you just swap out the set of scalars. And it's going to work exactly the same. So you will make an inner product, this time of polynomials. Your error is also being a polynomial now. This is also a polynomial. But in of itself, it's not that different. Now, one very nice thing, especially for me, who does FHE, is that LWE and all the others are additively homomorphic. So if you have two LWE samples of some messages here, you just write it out and expand it, etc. We'll see that just adding it component-wise boils down to actually creating a ciphertext of the sum. Because the usual inner product here is linear in the component, so these two just slip in there. And the implication is we can add things. Now, this is not just interesting for FHE, but also for public key encryption, because the regave encryption I just showed you was symmetric, but we often want public key crypto. So this works by just, publishing a public key, which consists of encryptions of 0. And to then encrypt something, we take these encryption of 0, We just combine them, more or less randomly, and then add the message to it. And that's it. And the private key still is the secret vector. Then, in cryptography, we often care about security notions and how to characterize the security or properties of schemes. So often, but there's a bunch of variants, we use these type of acronyms. So you'll say that a PKE scheme is in CPA secure. So what these acronyms mean is kind of seen here, instance or indistinguishable, for example. But now the question kind of is, what does that mean? I'm just gonna kind of go through it. So for example, there's a thing called in CPA games, or just a game, to determine whether a scheme fulfills this property. And for CPA, setting is kind of the adversary who wants to break the system has access to an oracle where they can query as many messages as they want. No matter how much. But the key point is this is just an oracle. This party may not have the key. And so eventually, the adversary is going to send me, who knows the key, 2 messages, M0 and 1. I respond with the encryption of one of them. And then it's up to the adversary to figure out which one I sent. At this stage, they can still query the oracle more often. But at the end, they're supposed to output a bit. And if this bit corresponds to the choice I made, they win. And the scheme is then considered secure in this game if the adversary can't do better than guessing, so just outputting a random bit on average. A stronger notion is CCA, so chosen ciphertext attacks, where the adversary doesn't just have an oracle to an encryption, but also to decryption. So again, Alice can query as many messages as they want to these oracles, then also sends me 2 challenges. I send one of them back, and Alice again tries to find which one I sent. The interesting point here is between step 3 and 4, Alice can keep on querying the oracle. So I actually need to tweak the game a bit so that it's not trivial. Namely, that between step 3 and 4, Alice can't call the oracle on the message I sent back. Because otherwise, they can just decrypt it and figure out which one it was. And again, if they can't do better than guessing, it's in CCA secure, more or less. Then, some other notable points. If you have a crypto system that's deterministic, it's not great for in CPA security, because then no matter what, if I encrypt the same message, I will see the same encryption. This may not be enough to invert it, but you can do a lot of analysis just based on that. For CCA, another interesting thing is if the ciphertext is tweakable, modifiable, in a way that I obtain a new valid ciphertext, then it's also not CCA secure, because go back to this game here. After step 3, if Alice can somehow modify the ciphertext I sent back, it's going to be different than the challenge I sent. And therefore, they could just send this tweaked message to the oracle, to the encryption oracle, and determine some information about it. This is also why it's almost impossible, or just impossible, to build FHE schemes that are in CCA secure, because you can always, well, add data. And there's a bunch of other notions. For example, there's in CCA 1, 2, 3 that differ in the details. So yeah. Another important component for these protocols we're going to see in a bit are hash functions. And this is a very simplified view, because there's also going to be more lectures on hash functions. And more or less, its hash function is a map taking an arbitrary length bit string and outputting a fixed length bit string. And should at least have these properties. So if I give you an element in a range, determining the preimage should be difficult. Likewise, if I give you an input-output pair, it should be also difficult to find another x prime, such that they map to the same thing. Note, the existence of that is basically guaranteed since we have an arbitrary length input. Finally, in general, it should just be hard to find 2 values with the same hash. But yeah, more on them in later lectures this week. Now, before we actually get to the main part, there's one last thing. If protocols use hash functions, eventually we still want to analyze the security of a protocol. And one way to do so is to just fix the hash function in a protocol and then analyze the whole thing based on the characteristics of this hash function. This works, but it's somewhat tedious, also because you need to then repeat the analysis for every hash function. So what's often done is analyze it in the random oracle model. And the idea is to kind of replace the hash function by something that behaves like a perfect one. So what it means, if I call this random oracle on some value, the hash function has never seen it before, just outputs a random value. If it has seen it before, just outputs the same one as previously. Takeaway here kind of is, no matter how often I query this random oracle, I don't really get information about my next query, so what the output of my next query would be. This makes analysis easier, but also leads to some interesting issues, which we're going to come back to in a bit. All right. So far, any questions? Yes? No? OK. OK, so key encapsulation mechanisms. So first, let's describe a bit of a setting. We want to set up a secure channel to communicate. So one option to do this is just to say, we all set up our keys for some public key system and only use that to communicate. Since the public key can always be published and anyone can send you a message, you can send anyone a message and only you can decrypt, and sure, why not? Well, problem is, most PKE systems will have very large ciphertext. On the other hand, they're going to be comparatively slow with regards to, like, well, if you compare them to symmetric schemes, they're much faster. The other option, kind of a hybrid, is to say, well, we use the not PKE scheme, but like a key encapsulation mechanism to set up a shared key. And then once this shared key is set up, we just use symmetric encryption for everything else, which is going to be much faster. Ultimately, really, what is the KEM? Like, this is a general blueprint. So the KEM is also going to have a public-private key pair. It's going to have a key generation step, an encapsulation step, which on the one hand outputs the shared key, and then also an encapsulation to be sent to the party having the private key. And the encapsulation method is just going to either output the same key, but it can and it's encouraged to fail if anything goes wrong. In general, KEMs will use PKE schemes internally, but it's not just going to be that like the encapsulation is going to be the encryption of the key. And to kind of see why you shouldn't do this, and it's also why I mentioned RSA earlier, we have this nice setting here. So we want to set up a shared AES-128 key for some block cipher mode. So what we could do is say, OK, Alice samples the key, encrypts it with RSA, sends it back, sends encapsulation back, and Bob then has this shared key. Problem is, this specific way of doing it actually enables new attacks on RSA. For example, meet in the middle, if for whatever reason this can be factored. It also impacts other attacks like hashsets, which kind of depends on the size of the message. And obviously, all other attacks about RSA still work. So in general, we don't want that. But this is not to say that you can't build a key encapsulation mechanism using RSA. It's just not going to look like this. Right. So now we're designing KEM, be it for NIST or in general. What goals could we have? Well, obviously, the whole thing should be secure. So it shouldn't be possible to just derive the secret key from the encapsulation of the public key. Then we also want some kind of theoretical notion, namely in CCA. We want the encapsulation to be fast. Likewise, we want the keys not to be too big, and the ciphertext not as well. And maybe, though this is very subjective, what it actually means, it should be difficult to mess up the implementation in a way that leads to side channels or other issues. Now, how do we do this? Now, a lot of PQC candidates used a similar approach, namely the Fushisaki-Okamoto transform. And very, very abstractly speaking, it's a general blueprint where you plug in something that's maybe just in CPA secure, specifically a PKE scheme, actually. And what you get back is something that's in CCA secure by using hash functions in a specific way. The original proposal was like for hybrid schemes in general, But the say version used for ML-KEM and also KEIBE is somewhat different and simplified. And all these references are also at the end, by the way. In general, it's kind of quick to describe. So what the transform takes as an input, some PKE scheme, and to hash functions. Key generation is effectively the same, although we're going to keep the random values used to generate the secret key. To encapsulate, what we simply do is we plug in some randomness we need. We sample it from RNG or elsewhere. We hash it together with the hash of the public key. This gives us the key and some more randomness. And then we reuse this randomness for the PKE scheme to encrypt same input randomness. And this is the encapsulation. And what the person decapsulating simply does is trace back the steps effectively. So on the one hand, obtain M prime back so they can compute K prime an hour. But then they also re-encrypt. The point of re-encryption is to make sure that everything went correctly and that no, let's say, shenanigans happened. If that's the case, so if C prime equals to the encapsulation itself, we output the key. Otherwise, the key is going to be set to the result of some hash. And this step is somewhat interesting, but this is for later. So this is the general blueprint. This is also what ML-KEM is based on. So kind of all we need now is a PKE scheme and hash functions. Let's start with the PKE scheme. So this is some math here. So again, we do module LWE stuff. So we have our polynomial ring up there. And the input for key generation is simply some module dimension. In the standard, the value of k kind of determines your security level. So you have different categories in the standard, and based on that, you would adapt this module dimension. And you also have some randomness as input. And the output, on the one hand, is the public key, which is a tuple of a matrix and a vector, and the secret key is S. Based on that, you can kind of already guess what's going to happen. First, we need to generate some more randomness. This is particularly important, actually. We sample a matrix uniformly at random from the space of polynomials. Do the same for the secret key. For this error term, we also sample it from TQ. Difference is we're going to pick a specific distribution. For ML-KEM, it's a centered binomial one, but the choice, you can have different choices and still remain secure. And then T is just, well, A times S plus E. So this is just a system of MLWE samples, which we've seen at the very beginning. Like if you just look at a row, it's going to be a vector of polynomials, and then the right-hand side is this B term for MLWE samples. Now in practice, the public key wouldn't actually consist of A, but this value rho here. Because if we seed our RNG with rho, then anyone can just recompute A. And then we don't need to transmit this whole matrix, saving quite a lot of memory. Yeah?
So for these different versions of the problem, do you use the same distribution? So on the error, so for RWE and modular lattices and
it depends a bit because, okay, for the standard, they only consider MLWE, so they only use centered binomial distributions. In FHE, it's more common to use discrete Gaussian distributions. But for security, it's usually enough to pick the same distribution as your secret key, if that's possible and doesn't lead to other issues. So for example, if you sample the secret key from discrete Gaussian, then you could use the same for the error, but you can also, I don't know, use error in Hall or some sub-Gaussian. There's a lot of literature about what you can use, but it's quite flexible. But when it comes to LWE, ring LWE, and module LWE, it's more or less the same. Because you can always reduce ring LWE to LWE. I can show you later. So you're quite flexible in that regard. No, okay. This is encryption now. So we have the public key. I just wrote A again because it's easier to follow. And we want to encrypt a message under some randomness. So what we're going to do here is we sample a bunch of more vectors of polynomials and form these terms. Now at first this is a bit illegible, but what happens here is, remember that the rows of AT are MLW samples. So if we now multiply both sides by transpose of y, we're just creating a linear combination of these MLW samples. At the very beginning I said MLW samples are additively homomorphic. It's also homomorphic with regards to scalar multiplication. Hence this is still going to be an MLW sample of 0. With potentially bigger error, but it's still an MLW sample. Which then means, consequently, oops, too quick, that if these terms here are MLW samples of 0, we just add a message, we have an MLW sample of m, and we're done with the encryption. Well, not quite, because again, we need to scale this if we eventually want to decrypt. In the standard, this is not quite the same, because this is not explicit. They achieve the same purpose by special methods called compress and decompress, which act the same, but simultaneously also shave off some bits of the encryption to make the ciphertext smaller. Decryption then is kind of boring, because it's just inverting this regap encryption from earlier. So a private key is necessary for decryption, it's just the secret in ciphertext. And if you remember the very first slides, this is just the vector here, so we're just inverting the MLWE sample, and then we also need to divide here by this delta to round the error away. But this is the gist. And so we have our PKE scheme. Well, let's just apply the transform to see what comes out. Now for the key generation, there's not much to say. The public key of the KEM is the public key of the scheme. The secret key is also going to be identical, except we also include now the public key and a hash of the public key, and this randomness used. This is a typo. This D and Z should be the same. Right? Encapsulation, it's really just filling it into the FO blueprint. So you plug in, so you have your hash function, and this is just substituted with the PKE encryption. Likewise, decapsulation works very similarly, so we plugged in the PKE decryption, PKE encryption. There is one notable difference. This J. The normal FO transform only needs 2 hash functions. The Kyber proposal also only used 2 hash functions. The standard introduces a third one. Make of that what you will. In practice, these hash functions are SHA-free, except for J, which is set to SHA-256. I went through the standard and not really. At least I couldn't really tell explicitly. Maybe there's a discussion on Google Groups somewhere, but because most of these discussions happen on Google Groups. Right? Now there's more differences with regards to the Kyber proposal. So beyond the difference I just talked about, there's more differences to the FO transform in Kyber, because they also use a KDF, so key derivation function, which does what the name implies. The full discussion as to why they removed it, etc., can be found here. Now there's also this comparison between implicit and explicit rejection, and this is with regards to this last line. Because implicit rejection would be that we always compute this hash here before making the choice. And the idea is that if we only compute it within the branch, this enables a side channel, because then we always know which one was chosen and can potentially attack it. The way the standard is right now, it's an explicit rejection, and the reasoning was kind of that it kind of impacts the tightness of some security reductions, but not necessarily in a really dramatic way. Final difference was in the original implementation, also the very first submission proposal. This randomness that was used frequently, like after sampling, would also be hashed. And the motivation was kind of to say, well, if you have like a really bad RNG, hashing might hide that a bit. The rationale for NIST to remove it was to say that whoever is implementing the NIST standard should always use a NIST-approved source of RNG, which is then going to be good RNG, hence this is pointless. And so also in the implementation, for the same reason, this was kind of called a hash of shame, because it kind of implied distrust of your system. Right. Now, important question to ask now, why was Kyber chosen even? Because here are other lattice-based candidates. I'm focusing primarily on those. There was Frodo, where instead of using MLWE, they chose LWE. NIST, and in general, this is often considered somewhat more secure, but it is significantly less efficient. So the encapsulated key tend to be at least 10 times bigger, in some cases up to 15 to 20 times bigger. Saber was a proposal with people also from COSIC. They relied on module learning with rounding, which is another lattice-based assumption. Intuitively, think of your LWE sample, you have this error term. With LVR, what you do is you don't actually have an error, but you divide and round the whole LWE sample. This is going to introduce some new error, but ultimately you don't really need to sample, which is quite nice depending on your system you're on. So even this said, there's like effectively no issues with this proposal in terms of like speed, security, etc. Like it's quite comparable to Kyber. So ultimately they needed to choose between the two because they only want to standardize one lattice-based proposal. And so what they did is to say that, well, MLWE is better understood than MLVR, and this is why we picked Kyber. And that was the official reason. There was also NTRU, which relied on an NTRU assumption, which was talked about in the last lecture. There, the keys were somewhat larger and generation was a bit slower, but in itself there were no major issues. So the whole thing is still secure, but kind of because of these reasons I preferred Kyber. There was also NTRU prime, which is a slightly different assumption, but still related, with somewhat similar issues. And so primarily these reasons are why this proposal wasn't chosen. And there was also some disagreement between the authors that claimed certain things about NTRU prime, where NIST seemed to disagree. Like the full discussion can be found here. It's like a bit long. So if you're interested to know, you can check it out. Okay. This was about KEMs. Are there any questions? Is everyone still with me? Beautiful. Then let's get to signatures. So first of all, what is a signature? For those who don't know, effectively, it's an approach to guarantee or prove authenticity of something. In the simplest case, you want to prove that, well, I really signed this document. It was me. Like, I accepted this document in its current form. So similar to PKE, it's associated with a public-private key pair. The private key in this case is there to sign things. Public one is there to verify that the signature is correct. And so a lot of people get a bit confused because they see RSA, and with RSA you can technically sign by swapping encryption and decryption. But this will not be true in general for any PKE scheme. In most schemes, this would not even make sense. All right, and so we can ask again, kind of what could be the goals to design a signature? Well, obviously, again, it should be secure in the sense that not anyone should just be able to forge a signature without a private key. It should be difficult to extract a private key, be it from the public key or from the actual signature. And a bunch of other notions. There's also games for signatures and so on. The important point is that the signature itself shouldn't be too big. For example, it would be really bad if the signature would be as big as the message you're signing. Likewise, the signing process should be reasonably fast. This is kind of interesting, and we'll see in a bit why. This is the very basic type of signature, kind of, but much fancier construction exists. So for example, you have ring signatures, where you prove that it was a certain member of a group signing the message, instead of really knowing who it was. There's also functional signatures, which are often used for zero-knowledge stuff, where you can sign a message only if it's like in a range of a function. So you can sign, for example, inputs to predicates. But we don't really care about those for today. Now, just for some history, lattice-based signatures are not new. It's been around since the 90s, and the first one came out in 95, if I remember correctly, was NSS. And NSS was assumed to reduce to n-true in a hard regime, which means that since n-true is parameterized by a bunch of values, it was thought that NSS, breaking NSS would involve breaking n-true for these hard parameters. But this didn't turn out to be quite true. So it was broken by Craig Gentry, also known for creating the first FHE scheme. And so it was shown that actually it reduces to a somewhat easy regime, which doesn't mean you can't instantiate it in a secure way, just means it won't be particularly efficient, in terms of size or speed. In general, and this is also mentioned in the last lecture, n-true is fine. It's often criticized in literature for being easy to misuse, but this is a moot point. It is secure in general if you use it properly. It is the first one. Since then, there's been a bunch of other lattice signatures, but they all kind of came with issues why, and then they weren't necessarily considered for the standard. They certainly inspired the standard, but it's not like the standard's going to be one-to-one one of those older ones. One issue, for example, is that on some devices, it's very hard to sample from discrete Gaussians. Difficult in the sense, it's difficult to do it in a way that doesn't enable side channel attacks. Then, the signature we're going to see is also a result of applying a transform. It's not the only signature that does that, and it's going to rely on something called a Fiat-Chemie transform. And the Fiat-Chemie transform is not just used for signatures, it's also often used in many other contexts. But for us, the transform is going to turn an identification scheme into a signature. Now, what is an ID scheme? The idea of an ID scheme is it's an interactive protocol that allows you to prove something. Specifically, you're going to prove something about yourself. For example, it can be identity. I am the one holding the secret key to something. It can also be used to prove knowledge of something, be it, for example, a zero-knowledge proof or a commitment, if you heard of that. So in general, it also comes with a key generation procedure. Then the first part is going to be called a prover. It's going to commit and respond. And then finally, there's a verifier, which, verifies things. In general, this is what a run looks like. So first, the prover would commit to something, send a commitment. The verifier then sends some kind of so-called challenge. Often it's just a bit string, but it doesn't have to be. In case of a signature, it won't be. Then the prover generates its response based on that, sends it back, and then it's going to be verified. In general, the scheme is considered sound if the verification being true implies that the statement to be proven holds. And so the Fiat-Chemie transform is going to take an ID scheme like this, and it's going to transform it into a signature scheme. And it's quite straightforward. This is how it would look like. So the signature method itself would just be, OK, if needed, you sample some randomness. Just apply the commitment from the ID scheme. You then hash the commitment and the message, then derive the response, and then your signature is just the commitment and response. To verify, well, since the verifier now has the commitment and response, they can recreate the challenge. Nice. And then run the verification algorithm of the ID scheme and return a response. Now, intuitively, what you can say is that the Fiat-Chemie transform is going to replace the challenge by the result of a hash. And the motivation is kind of to say that if we analyze this in this random oracle model, well, the hash function is going to behave randomly. So in essence, it acts like a random challenge by another party. And so this construction is considered secure in the random oracle model. But now the actual interesting part. Is it actually secure if we instantiate it with a concrete hash function? Now, since I'm asking, what can you guess? I heard it somewhere. Yes. So it's not quite clear. So on the one hand, you have really old papers that show that you can construct an ID scheme for which, if you replace by any hash function that's computable, it's going to be insecure. Now, if you read the paper, this is a very convoluted example. Something that's more relevant is something that actually appeared this year, is that if you use the transform to create zero-knowledge proofs, you can run into issues. Specifically, they show that like if you have a concrete proof system that uses Fiat-Shamir, you can mess it up in the sense that it completely breaks. The arguments don't quite carry over to the signature setting, because what happens in proof systems, often you're going to prove a statement, and that's going to include a hash of the context. And if instead of including the entire context or just the hash of the context, this is going to create the security issues from that paper. All right, but for us, it's fine. So another tweak we'll need, because it's not quite the normal Fiat-Shamir transform we're going to use the one with the boards. And the idea was actually introduced for lattices by Lyubashevsky. And then kind of ideally, if we have an ID protocol run, it makes sense that a verifier should always accept like a valid response. So if everyone is honest, why should this fail? Well, the idea is to still introduce aborts now. So the prover can now, at the response stage, say either return a response and send it, or I abort the protocol. Question kind of is, why are we interested in that? Well, the ID scheme we're going to use, it puts some restrictions on the signature, or let's say commitment and response themselves. And so to make sure that these restrictions hold, the protocol is going to check whether the signature is response is in a certain domain, and if not, it aborts the protocol. This is necessary for security, but it's also necessary for some correctness reasons. But now, without further ado, let's actually look at the simplified version of the ID scheme used. There, the input is some randomness and 2 modular dimensions this time. And then you sample 2 secret polynomials, one with modular dimension one from a module of dimension k, one with dimension L. And you kind of construct a verification key like your usual MLWE system. And indeed, this verification key is an MLWE samples of 0. Okay? Now, what do the provers and verifiers do? To commit, what the prover does, it samples now 2 random vectors, again, of polynomials from a special distribution, and computes, again, a system that's very similar to the previous one. The challenge in this protocol is then a single polynomial from the space, and it's sampled in such a way that the coefficients are considered small. In the standard, there's a parameter determining what the maximum coefficient value is, and this is ultimately what's then being used to bound C. The response of the prover is then just this first polynomial plus C times S1, so the first secret polynomial. And then what happens during verification? Well, on one hand, the verifier will check, well, is that in a certain range, or is it small enough? Because it should be small, since everything we picked here is small. And on the other hand, it's going to compute this V prime here based on a response it got and check whether these 2 are sufficiently close. Now, there's a first question here, and I kind of said it, where is the board here? Because I said we use Fiat-Shamir for boards later, so the ID scheme should have a board somewhere, and it's going to happen here. Oh, sorry, up there. Because the prover is also going to verify that Z is small, and if not, it aborts the protocol. Because if Z is not small, it can actually be shown that Z then will leak something about S1, which is what we don't want. So yeah, if Z is outside a certain range. Now, this wasn't quite as clear as the encryption itself, so you may wonder, why does this work? So if we write out both terms, so this W and W prime, and just kind of compare them. So if we now take the difference, these A times Y1 terms disappear, and we're left with Y2 and C times S2. By constructions, these were all sampled from distributions that make sure the coefficients are small enough. So if everything went correctly, then indeed the difference is quite small. Difference is quite small, and the check passes. Now, we can just apply the phi HME transform. Now, I skipped key generation because it is the same. Yes, it's the same. For signing, we kind of just fill it into the transform. So here we build our commitment. We hash it, but not with a normal hash function, but a special one that outputs values which are polynomials in this ring. And then again, we build a commitment. And then again, we do this check if it fails. So if it's aborted, then we restart. Like we resample y1 and y2 and repeat the whole process until we eventually find something that passes all checks. And eventually we return, well, the signature, but also the hash of W and mu. Mu is not on the slide. And we also haven't used the message. So this seems like kind of a pointless signature. But the point is actually that we're going to use mu, which is going to be hash of m and actually also other things, to seed the RNG used to sample y1 and y2. And this will then also ensure that like the message is taken into account during the signing process. Then verification is effectively equivalent to the ID scheme. I say effectively, if you read the standard, it's not going to be. Because all these things I actually just discussed are more or less implicit in the standard. So for example, what's happening in the verification step is based on the signature, we actually recompute C tilde and compare it to the one in the signature. And the verification would pass if the values match, and otherwise it wouldn't. Likewise, the actual signature is constructed in such a way that we drop the least significant bits of each coefficient in these polynomials. But at the same time, we will provide something called a hint, which kind of still allows you to recompute C tilde. And in general, there's a lot more hashing happening than just in a phi HME transform, also to make this whole thing more efficient in terms of memory. All right, so like with Kyber before, we can ask, how different is MLDSA from the dilithium proposal?
Can I ask a question?
Yeah.
Because it's on the hint. So
Yes.
like, yeah, because of the history of hints that were used to break some stuff.
Mm-hmm.
So what do we know about hinting here?
In terms of security, etc. The hint is not really there for security here. So they say that it doesn't really impact it. But I'll be honest, I'm not knowledgeable enough to really discuss that. But the hint is mostly there really to just make it smaller. And it also doesn't leak anything about the secret. Like it's not even used for that.
Okay. Because I guess like yeah, for the lattice-based schemes that were like broken because of hints. So I guess like it was like a lot stronger hints.
Yeah. Another reason this works is because by shaving off these LSBs, you kind of introduce some more noise. So it doesn't necessarily improve the security, but it doesn't always degrade it either. All right, so are there any differences to the dilithium proposal? Yes, but they're not as big as with Kyber. So for example, in the proposal, certain parameters were used, which were later on tweaked for the proposal. Most of the time, they were increased if NIST cared more about security. But in a lot of cases, stay the same. Another thing is that the original proposal of dilithium was deterministic, so the very first one. MLDSA is not, so it introduces more randomness, but you can actually use it in mode that's deterministic. And this is also included in the standard with the rationale that sometimes you don't have access to a good RNG source. Okay, now very briefly, why dilithium? Well, first thing to note is it's not the only one that got standardized. There was also Falcon and Sphinx. And dilithium in general, the selling point was it's a good trade-off between like everything, security, efficiency, and the theoretical justification. But then, for example, there was also Falcon, where NIST says it should be preferred if you care about small keys and signatures and fast verification. But they also claim, though they just stated it without a lot of reasons, that it's more difficult to implement in general. There's also Sphinx, which is not based on lattices, but rather on hashes. And I assume it's going to be talked about this week as well. And then there were other proposals in the third round which did not use lattices, so I didn't really mention them. But some of which also had issues. Like, for example, Bart also mentioned it, Rainbow was broken completely, and so NIST doesn't really consider it anymore. And so this was kind of then the lithium. Are there any questions about that? No? Well, and very briefly, some concluding remarks. So as I said at the beginning, depending on who you ask, quantum computers are relevant already today, or never will be. I guess the truth is somewhere in between. But it's best to already change things now. Then maybe like two last slides, which are not necessarily quite theoretical. I think a lot of people here are familiar with XKCD. And so the idea kind of to say is like, all this PQC stuff, well, here it's RSA, is really cool and really secure. In practice, if someone wants your data, they're just gonna, well, start harassing, if not beating you up. And I'm not mentioning this just as a joke, but also because your PQC algorithms can be as good as you want. If your backend is flawed, it's not gonna help you. If your device is backdoored, see UK, then you can use PQC wherever you want. In the end, people will still get your data. Because even if you implement backdoors, there's probably someone smarter who will also find them. But yeah, this was briefly it. The slides will be uploaded, so if you actually want to read these articles, you can. And if you have any questions, well, you can ask me now or later. Thanks.